Good morning, neighbors. Beautiful Saturday. Waiting for a contractor to come to the house here, do a bit of work. So, what's up? How's everyone doing? Well, I hope. It appears my COVID shot is helping something, somehow, somewhere, maybe. Still waiting. I got the J&J single shot. I've heard of a booster coming out for it, and just kind of waiting for when that's available because we know how these things work. Generally, have a pretty good idea or can learn about how these things work. That's the hardest part. Anyway, energy at a distance. Energy at a distance. What does that mean? These are massive theoretical equations when you get into understanding energy transmission, energy, how it moves. Electricity is one of the most common we know about, kind of understand, right? Electrical current through the walls, 120 volts powers your electrical outlet. That we know about, know quite a bit about. DC voltages, like from your battery. From batteries, they put out a DC voltage, not AC. To make them into AC, you need an inverter or a converter of some sort to make it into an AC power source from your battery. So, we've learned how to do these things very well. But energy at a distance equations, what would those look like? This one's tough. It's kind of like you can do throwing a ball, depending on how you throw the ball, the arc of the ball in the air. There's equations for how much energy that ball is going to have when it hits the ground on the other side of the throw. There's equations that describe which direction the ball is most likely going to go. You get into some probabilities, because when the ball bounces, did it land on a rock and maybe deflect away from where you thought? So, energy at a distance. Now, this comes in to all types of energies we can talk about, right? Sound. You know, the further away you get from the speaker, the quieter the sound gets. You know, when you go through a doorway and around a corner, the sound changes. It might reverberate. It might even get louder at some points around a corner, which is very odd, but it's a fact of acoustics. So acoustical engineers would know all about audio waves, how they travel, where they travel. If you go back and look at how cathedrals are designed. Yes, cathedrals. There was an engineer involved in that, doing acoustics for how the organ will sound and where the sound will go, or singers on the stage, or even the pastor or preacher, whoever's up at that pulpit spieling whatever they spiel, right? That volume, that sound, how it carries is a matter of physics and equations, and can be described orally. Yeah, it was loud. It was really loud. It was super. It hurt my eardrums. So what does this have to do with nuclear? These energy at a distance equations. They apply to everything. It's kind of incredible if you start to look into the details of how energy moves around, how light moves around, how light creates shadows. Light is a form of energy, and it has some rules. Light changes speed. The speed of light is not constant. It's constant in a vacuum, and that's a theoretical vacuum at that. But all the theories put together still work. They're being tuned, they're being improved, but the fundamentals have been pretty well understood for a long time. So energy at a distance, why does this matter? Because the conversations about it get very convoluted. When you talk about radio frequencies at a distance, the closer you get to the antenna, the more energy you're feeling. Whether you're conscious of it or not, your body is absorbing more energy from the transmitter. What your body does with that energy, how it absorbs that energy, how it interacts with it is very important to understand. A microwave engineer will not climb a tower that's energized. Generally speaking, there might be rules otherwise, but to get that close to those transmitters is harmful, period. The distance from the source of the energy matters. It is a matter of physics, it's a matter of chemistry, it's a matter of biology, it's a matter of energy traveling through mixed media, different environments. The humidity in the air matters to these equations. The amount of debris in the air matters to the equations. So when you see a radar set and you envision that blast of energy coming out of that radar horn, a pulse in the megawatts or gigawatts of high frequency energy pulsed out into the ionosphere or the atmosphere around, and as it travels, as it propagates through the atmosphere, its speed changes, its properties nominally change, and there's equations that describe all of these things. It is truly incredible. Equations that describe how radio waves travel through the different layers of the atmosphere and the amount of infraction or inflection or deviation, attenuation acquired through that travel. There's equations for that. For radar, you're looking for what bounces back from that signal you just blasted out. You're measuring the time intervals into microseconds, even picoseconds, with some of the detector speeds that we're at now. Sampling so fast, it's beyond imagination, yet it's real. This is a world of energy measurements, very specific instruments. Almost every type of energy measurement has a specific instrument required for it. You might know one of those instruments is a voltmeter. It can measure AC or DC voltage. There's specifications for the frequencies it can measure accurately, because as frequencies increase, the rules inside the electronics, the meter, even the probes, changes and has to account. The user has to know what the capabilities of that meter is, or he's wasting his time. So these energy travel equations, energy at a distance, it's the fundamental principles radar relies on. And in order for radar to work properly, how that wave propagates through the air has to be understood, and is very well. The interaction of the frequencies transmitted with other molecules is actually mapped and described out. So these conversations that 5G is safe is marginally true, is mostly true, is probably true. There are discrete measurements that can be taken for this. There's training that can be taken for this that can show you the harm, because you have to know about it if you work in these fields as an engineer. You don't have a choice. It's a matter of life or death. It's a matter of life or cancer. It's a matter of some disease being caused by the energies that you're working with. Now, oddly, you can get those energies expressed in chemistry, in biology. There are many different measurements of energy. The ERG is one of them. It's worth looking up just out of your curiosity. ERG, unit of energy measurement, used in molecular biology mostly. Very tiny increment of energy. Talking about the transfer of energy between molecules. Those are ERGs. People that talk in ERGs generally know what the ERG is and know how to talk about it. So, there's another ramble Saturday morning. Hope you all are well. If you got a topic, put a note down below, please. Peace is out. Thanks for listening.